Hi, my name is Jason Mears and I'm going to take you through VMware Enterprise Blockchain. What is a blockchain? So, it's a chain of blocks, but probably more helpfully, it's a chain of blocks that are all mathematically linked to each other to guarantee the integrity of the information contained within each block. So, I'm going to oversimplify a lot of stuff here and we'll build up increasingly as we go through each slide, but just for now I'm going to treat a block as just a block of information. So as you can see on screen there, we have block 1, and each block contains data. At this point we're not validating any of the contents of that. If that data was to get edited, manipulated or corrupt, we wouldn't know any different. We just know that there's a block full of data. And each block is added to the chain independently of the others. So as I add block 2, block 3 and block 4, I'm slowly building out my blockchain. So this is in essence what a blockchain is. It's a chain of blocks that are incrementally added in a linear fashion. Now the first block I showed you just contained a block of data. There was no validation whatsoever that the contents of that block hadn't changed. Now in this new improved block, you can see down at the bottom I've got a signature for this block. So there's a signature for the data contained within the block. Now again, this is an oversimplification. I'm just going to call it a signature. What it actually is a hash or a checksum, but it's basically something that just says the information in that block matches up or validates against this signature. So now that each block has a signature attached to it, we can identify errors with accidental corruption, but it won't protect us from deliberate modification. And the reason that this signature doesn't protect us from deliberate modification is whoever modifies the data in the block could equally modify the signature accordingly, so that although the data has been changed, the signature still matches because we've kind of doctored or kind of modified the signature as well. So here's my first block. I've got the data in the block and a signature, and the data and the signatures match, so I've got a green tick or check mark at the bottom there. I'm happy with this block. And I can do the same for block number 2 and block number 3. Again, I'm creating a blockchain. So in this example, every block contains a valid signature for the data contained in the block. The signature here corresponds to the data in the block here, and so forth for this block and this block. So from a validity point of view, everything looks okay and everything is okay. So that's just a sequence of 3 blocks where everything is okay. What I'm now going to do is run through that again. So again, first block looks okay, signature matches the data in the block. But what I'm going to do on block 2 is somebody's going to modify the data inside the block. So you can see from that red pencil, somebody's modified the data. So they've changed the data here, but they haven't changed the signature. So the data's changed and the signature doesn't match. So now that block looks like it's invalid or corrupt or has been tampered with. I move on to the next block. This block again knows nothing about any previous blocks or subsequent blocks, so it just knows that it is okay. The data contained in the block and the signature look okay, so that's okay as well. So what we've got here is 2 blocks that are good and 1 block that's been edited or modified and looks invalid. So if this was an accident where this data had accidentally got corrupted, we would have a means of knowing something's wrong with this block. We might have to check that data because the signature doesn't match. So that's how we're protected from accidental corruption. Something looks wrong and something is wrong. So we've got an accidental corruption, but it's obvious to us that something's wrong, so we can actually go and check it. So here's another example. So this time we're actually going to show somebody deliberately corrupting the block. So first block looks fine, the data and the signature match. But what's happened on this second block is somebody's not only modified the data in the block, but they've also modified the signature. So even though this block has been tampered with, because the signature and the data match, it appears to be okay, even though it isn't. And on the next block, again the data and the signature appear to match, so it looks okay. So first couple of issues here is this block has been tampered with and modified, and we haven't realised because whoever's modified or tampered it has changed the signature, so we're unaware there's a problem here. And all subsequent blocks built on top of this block look particularly valid as well, because they only look at themselves in their isolation. So not only have we not noticed that this problem has occurred, we haven't noticed the insertion of or modification of the data in the first place. So as it says here, somebody's tried to maliciously tamper with it and disguise the changes by changing the signature. So everything looks okay, but something is definitely wrong here. So you can see from this that this is not secure enough to use in a business environment or a consortium, because it is possible to tamper with the data, and as long as you modify the signature you would get away with it, or it would be hard to detect that this tampering has happened. So what I'm going to show you now is the new superhero block or kick-ass block, which has some additional features built into it. So we've still got the data and the signature for the block, but we're now going to include the signature from the previous block included in it, and we've now got a magic number or nonce because this block is additionally protected by a mathematical puzzle. So as I said before, we've added a new feature is the signature for the previous block, so it now has an awareness and a link to the previous block. We still have the data and we still have the signature for the block, but we've also got this additional magic number or nonce. Now the reason it's called a nonce is that it's a mathematical term that means number only used once. And the reason we have this nonce is that before we write the final signature for this block, there's a mathematical puzzle that we have to solve. And the puzzle consists of taking the signature we got from the previous block, the data itself, and this magic number here. This magic number is something we combine with the signature from the previous block, the data, and we perform a mathematical calculation on it, and we try with random numbers. So we might start with number 1, perform the mathematical calculation and see if the answer meets the criteria for the puzzle. If it doesn't, we try number 2, and we go all the way through picking random numbers until we find a number that meets the mathematical criteria to fix the puzzle. And once we've found that number, we can write that magic number or nonce there, and then by incorporating that magic number with the data and the signature from the previous block, we can then write a valid signature for this block. So the important part about that is we link it to the previous block, and we now have an additional magic number or mathematical puzzle which is very difficult to solve, which means if you're going to modify the contents of this block, you've got to solve this puzzle again before the next block is built, otherwise it's going to appear invalid. So I often liken this to like a very extreme example of Sudoku, where there's only one number will fit in that square to make this puzzle work, but whereas in Sudoku you're looking at a number which is between 0 and 9. These numbers here to make this puzzle work can be anything up to 64 characters long, so a massive amount of possible options and a massive cryptological puzzle to solve. So, but what that does is that gives us some security, and I'll walk through an example with this superhero block just to show you how that works. So here is our first block, where we've got the signature from the previous block, the data, and we found this magic number which makes it work and incorporated that, so we can finally seal this block with a signature for it. So this is a valid block that has a magic number in that slot, as well as a reference to the previous block. Now the second block that's built takes the signature from the first block and incorporates that, plus the data, plus a magic number or nonce, to perform a mathematical calculation to make sure that we solve the criteria for the puzzle. And once we've got that, we can then write the signature for the block and seal it as a valid block. And then the process continues, where block 3 takes the signature from block 2, sticks that at the top, combines that with the data in the block and this magic number or nonce to solve a mathematical puzzle, and once it's done that, it can then write the signature for block 3, and that's a valid block, and so the process continues. So what we're really saying here is we've got valid signatures or hashes, as they're known by mathematicians, for data contained within the block. Everything looks okay and everything is okay, and the important part here is that now that every block is mathematically linked to the previous block, which just makes it more and more difficult to tamper with. And I'm going to show you an example of what happens when somebody does try to tamper with that block. So again, we've got our first block, which is valid, and then on our second block, somebody's decided to modify the data here. Now what they want to do is modify the data. They also need to modify this signature, but it's not just as simple as modifying that signature, because we now have to regenerate this mathematical puzzle, taking into account the previous block signature, the new data, and a new magic number. Now solving this puzzle can take a lot of time. It can take up to 10 minutes per block in a cryptocurrency environment, and whoever modifies this block needs to be the first person in the world to be able to find that new answer to the puzzle, change it on this block and all the other blocks before anybody else realizes and builds a new block on top of this. So it's unlikely that an attacker can modify the data, fix the block and the signature by finding a nonce that works for the puzzle before anybody else builds a new block on top. Now, just as an example here, what the attacker's done is modified the data but not managed to find the magic number which fixes it in time, so that block is invalid. Now this block here next to it hadn't had anything tampered or messed around with, but because the signature for this block is dependent on the block before, because this one has been tampered with, every subsequent block is also marked as invalid. So we found a way of identifying modified or hacked blocks, but we've also found a way to make sure that anything built on top of that hacked block also is flagged as being invalid. So just as it says here, the second block has modified data without a modified signature, and without changing that magic number or nonce, the puzzle no longer works, and this now looks invalid. And because of that, any subsequent blocks also look invalid. So everything looks wrong because something is wrong. So it's not just difficult to tamper with this, but it's tamper evident. So we talk about tamper proof and tamper evident. Tamper proof means it's hard to modify with it. Tamper evident means it's easy to tell that somebody has tried to modify it. And the problem here is that modifying a block without fixing the nonce not only invalidates that block, but all the subsequent blocks in the chain. So here is where this security comes from. It comes from linking the signature from the previous block to the next block, and by incorporating the data and this magic number or nonce and this mathematical puzzle, and the fact that once this block has been built, all subsequent blocks follow on it again. So that was just a single blockchain. But we talked about blockchains being in consortiums, where you might have 6 different organizations that all maintain their own copy. And in this example, I've got 6 organizations, all with a valid copy of the blockchain, but for some reason, the blockchain E, this is the one that the attacker has tried to modify. So not only is it blatantly obvious that this is the one that's been tampered with or modified, even if we hadn't noticed that this was invalid, we can see that every other blockchain in the consortium has a different set of information or a different set of data. So not only is it easy to detect modification, it's very hard to get away with it because the majority of other members of the consortium all have a different version of the blockchain. So it becomes apparent that this has been modified with, and these hold the true copies of the blockchain. So not only was it difficult to try and hack this copy or modify this copy, if this attacker wanted to get away with it, they'd not only have to fix or doctor this copy of the blockchain, they'd need to do it with at least half of the other members of the consortium in order to stand any chance of getting away with modifying this data and nobody noticing that it's been tampered with. So I guess what we're saying is it's hard to modify a block, and if you do modify a block, it invalidates all the subsequent blocks, and even if you manage to corrupt that one and get away with it, the other copies of the blockchain in the consortium are going to highlight the fact that this one is incorrect or invalid. So it's a tremendous amount of work and mathematical processing and investment in equipment and time to not only modify a single block, but what you actually have to do is modify every copy of that block in every member of the consortium, or at least 50% of the blocks in the consortium, in order to stand any chance of getting away with it. And as soon as the next block is built, which could only be a fraction of a second or a couple of seconds later, it's too late. If you haven't managed to fix the block or corrupt the block or kind of patch up the block before the next block is built, you've been caught and you won't get away with it. So as we say here, one copy of the blockchain has been tampered with. Copies A, B, C, D and F are okay, but copy E has either become corrupted accidentally or maliciously. Either way, we know that we can't trust that copy of the block. And what we're saying is the blockchain as a whole still maintains its integrity, even through accidental corruption or malicious or deliberate actions. So this is why we talk about it having integrity, and why it's tamper-proof and tamper-evident in a way that traditional stores of information and databases just aren't. So, a few key points before I just wrap up. A block, it's the unit of which new data is added to the blockchain. A block consists of data and signatures, or to use the proper terms, checksums and hashes, and any other cryptographic information required to validate the contents. Hashes, these are the digital signatures used to generate a fingerprint for the data and any other information contained in the block. Nonce, or a number only used once. It's the number added to provide a solution to a mathematical problem that is used to guarantee the integrity of each block. This is the magic number, or the kind of incredibly difficult version of Sudoku. And we use linked blocks. So each block in a blockchain is linked mathematically to the previous block, which is in turn linked mathematically to the previous block. This is why it's so difficult to tamper with or edit the blockchain without breaking the maths behind it. So they are probably the key points to understand around what a blockchain actually is. And then just one side I thought I would throw in for anybody who's familiar with cryptocurrencies and how this might correlate with something like Bitcoin. I've used very simplistic and overly simple ways of explaining this, but I thought if anybody does understand cryptocurrencies, it might be worth just explaining the parallels. So where I talked about signatures in the Bitcoin network, that's actually a SHA-256 hash. And where I talk about the magic number, or nonce, this is effectively what Bitcoin miners are competing to find before anybody else in the Bitcoin network, because if they find the magic number that seals or validates the next block, they earn a Bitcoin or a number of Bitcoins for doing so. The issue, as we've discussed in previous videos, using this in a business environment, is this kind of mining, where you're using this proof of work to mine blocks by finding these magic numbers, is very, very expensive in equipment and energy. But again, that last slide was just to correlate and show you the equivalence of the terms I've used in this video and terms you might understand from any blockchain or Bitcoin experience you might already have. So, if you want to find more information about this, there is an accompanying guide written by the National Institute of Standards and Technology. It's called the Blockchain Technology Overview, and the relevant sections will be 3.6 on blocks and 3.7 on chaining blocks. So I hope you found this useful, and thank you very much for your time.